Hello, everyone. I'm Wei Chongqin from Renmin University of China, and I'm honored to be here to present our paper, MoRE, a mixture of reflective framework for large language model-based sequential recommendation. And I will begin with the background and motivation of our work. Let's start with the basics. And sequential recommendation aims to predict user next item of interest based on their historical interaction sequence, like clicks or purchases. The core challenge here is to capture users' interest currently. And recently, large language models, or LLM, has shown great promise. However, existing methods to incorporate them into recommendation systems have limitations. Some use LLM only for the feature embedding enhancement. Others use a traditional recommendation model first and have an LLM ranker, which limits LLM potential to analyze or reasoning. And while using an LLM as an entire recommender system is possible, but it comes with very high training cost. And to address these issues, we look to the reflection-based workflow. Here, LLM works in two stages. Offline, it analyzes the user's history and generates the reflection. That is the high-level summaries or insights about users' preference. Online, these reflections are used to guide the LLM recommender to improve its suggestion without the need for expensive fine-tuning. This approach leverages the LLM reasoning and analyzing capability while being cost-effective. And however, this reflection paradigm is not perfect. We identify two issues. First, it often ignored variable collaborative filtering signals, which is variable information from similar patterns. Second, the reflection strategy is often static, with a fixed pool of reflection, which limits the model's ability to continuously self-improve. And to solve these problems, we propose our framework, MoRE. MoRE stands for a mixture of reflector. It consists of two main components: multi-perspective reflectors, which generate reflection offline, and a meta-reflector, which evaluates these reflections offline and select the best reflection perspective for online usage. First, let's talk about the offline generation. To get a comprehensive understanding of a user's preference, we generate reflection from three different perspectives. Perspective one, we captured explicit preferences from item titles and descriptions. And perspective two, we focus on the sequence of site information, such as brands or styles or categories. And perspective three, we incorporate small collaborative filtering model for LLM to generate CF-based insights based on the CF rating from the model. And next, we need a way to ensure our reflections are high quality and improve over time. Our framework introduced an offline self-improvement iteration loop. We evaluate each reflection by measuring its impact on recommendation performance. High-performing reflections are kept and refined, and then we sampled the good reflection as the example to guide the LLM reflector to generate next round reflection. And so that creates a cycle for continuous improvement. Now for the online stage, with multiple reflection perspectives available, which one should we use for a given user at a specific moment? We model this as a contextual bandit problem. We use a lightweight RL model to select the most suitable reflection perspective, be it perspective 1 or 2 or 3, based on the user's real-time state, and ensuring the best possible guidance for the final recommendation. And now let's briefly look at our experimental results. Our experiment on the 3 Amazon review datasets showed that MoRE achieved a significant improvement boosting performance by 5 to 10 over state-of-the-art LLM for REC baselines. And for ablation study, we find that simply concatenating all reflection perspectives performed worse than using even one single perspective. This confirms that selection is necessary. And second, our RL-based selection outperforms a simple greedy selection or random selection, proving the effectiveness of our selecting approach. And in terms of efficiency, MoRE has a much lower computational overhead compared to the baseline that require fine-tuning the LLM. We also verified that our iterative reflection process works, and as the quality of reflection and the overall recommendation effectiveness generally improve with each iteration. And next, I will briefly mention our next iteration first, and then conclude the presentation. And before concluding, we briefly share our new works on the reflection-based recommendation with LLM. And via gradient descent, we offer new insight into the reflection working mechanisms. So welcome to follow up. And in conclusion, we propose a framework that leverages LLM's analyzing and tool calling capabilities for recommendation without the need for fine-tuning. Second, we design an offline reflection iteration loop for self-improvement to deepen user understanding. Third, we introduce an online perspective selection mechanism for real-time reflection usage. So I think that's all, and thank you.
Chen Zheng asks, would generating multiple reflections drastically increase costs, and how many reflection variants would be needed?
How much?
So would generating multiple reflections drastically increase cost?
Yes. It increased the cost, but all of the generation is working offline. So for online, we can just select which way we go, so which direction we chose, and for the final recommendation.
Okay. Jakub Fake is asking, what is the inference latency? Is it feasible for an online usage?
And so in our setup, we have an serving LM recommender. So this is the training or the computational overhead. And in the inference stage, we just use the reflections as the prompt input to the serving LM. So I think in different scenario, the way we use the reflection or the LM analysis is flexible, and you can just use the reflection or the LM analysis for the user. For the model input, you can convert them into the tag label, or you can embed them embedding them into the dense vector to concatenating into your model's feature. So I think all of the way can use the reflection. So this setup just one of the way to show the reflection's effectiveness.
Thank you for the talk. I had a question about the reinforcement learning part, or the feedback loop part. Do you fine-tune or learn the feedback on a global LLM model, or is there a LLM per user essentially at some point that does reflection?
And for LLM, we haven't fine-tuned them, and all the training cost here is for the RL model.